In this lecture, what I want to do is take some of the concepts that we've talked about in one dimension and extend them to 3 dimensions, okay? So let's talk about how we want to go about doing that, okay? So to extend the 1D viscoelasticity solutions to 3D, we want to consider the types of deformation that occur. So we consider the types of deformation, okay, that might occur. All right. So what are the kind of the 2 broad classes of deformation? Number 1, we could have what's called dilatation. Okay. So dilatation. And what is dilatation? That's uniform expansion or contraction with no shape change. Okay. So this is uniform expansion or contraction with no shape change. The second type of deformation we could have is shear deformation, right? Okay. In the case of shear deformation, that's shape change with no expansion or contraction. Okay, so, okay, shape change with no expansion or contraction. Okay, so this is certainly topics that we've talked about previously. If you're in your mind thinking, well, maybe we can decompose the stress and the strain into the spherical and deviatoric components and capture both of those, you'd be absolutely right. That's where we're headed. Okay, so what we want to do is we want to split the strain into dilatational or a spherical component and a deviatoric component. Okay, so we begin by splitting the strain, or decomposing if you like. So we decompose the strain into a dilatational, and I'll put in parentheses that's spherical, and deviatoric component. Okay? So what does that look like? Well, that looks like epsilon ij. To get the spherical component out, we just take an average of the trace, or the sum of the diagonals. So that it becomes 1/3 epsilon kk delta ij. Of course, then it's plus epsilon ij, and then we just subtract off the same amount, minus 1/3 epsilon kk delta ij, right? I'm going to put a parenthesis around that so we know that that's a separate component. So this component is the dilatational component, okay? And we're going to call that E sub ij. And this is the shear component, the deviatoric, right? And we're going to call this eta sub ij. Okay, so maybe I should put it under here. This is spherical, and underneath the shear, this is deviatoric. Okay? Let's go ahead and call this equation 1. And I'm also, so I can write this as Eij plus eta ij, right? So there's our dilatation and shear components. Now let's go ahead and think about Hooke's law. Okay, so I'll just say recall Hooke's law. This is for a 3D material. So not something quite as simple as sigma equals E epsilon, but in tensor form, Hooke's law looks like sigma ij is equal to lambda epsilon kk times delta ij plus 2 mu epsilon ij. Okay, let's call that equation 2. So remember that mu and lambda are technically what's referred to as Lemay constants. And mu, that Lemay constant, happens to be the same as the shear modulus, right? Okay, so let's go ahead and consider the case now where we have only a shear strain, so a deviatoric strain only. Okay, so let's go ahead and consider the case of pure deviatoric strain, or pure shear strain. And so we would say that epsilon ij is just equal now to eta ij, where we could write that eta kk, or epsilon kk equivalently, is equal to 0, right? The trace is 0 for that. Okay? So we may then write equation 2. Okay? So we may write equation 2 then as sigma ij is equal to epsilon kk, which is now equal to eta kk, which we said was 0 because it's deviatoric. That term drops out entirely, and we're left with 2 mu times eta ij. Let's call that equation 3. Well, what does equation 3 tell us? Well, equation 3, what does it look like? On the left-hand side is the stress. On the right-hand side is a deviatoric strain that's multiplied by a scalar constant. That scalar constant is 2 mu. So what we can say is that if we multiply a deviatoric tensor times a scalar constant, we are left with a deviatoric tensor. So that a deviatoric strain yields a deviatoric stress via Hooke's law. Okay, so that's sort of the takeaway from this. So let's say that because equation 3 yields, let's say, a stress that is a scalar multiple of a deviatoric tensor. Okay, the stress is a deviatoric tensor. Okay, so what does that mean? That means that sigma ij is actually Sij, right? The deviatoric stress tensor. Okay, so we can write then that Sij, the deviatoric stress tensor, is equal to 2 mu times eta ij. Let's call that equation 4. Okay, now let's go ahead and consider a pure dilatational strain. Okay, so consider a pure dilatational strain. Okay, so in that case, we're going to say that the strain epsilon ij is just equal to Eij, right? And so what happens when we substitute that into Hooke's law? Okay, so substituting into 2, okay, then we end up with sigma ij is equal to lambda. What is, let me write this down. What is epsilon ij, right? So epsilon ij is equal to 1/3 epsilon kk delta ij, right? So this term epsilon kk delta ij must be equal to 3 times Eij. So in this first term becomes 3 times Eij, okay? Then plus 2 mu times Eij, which is equal to 3 lambda plus 2 mu times Eij. Okay, let's call that equation 5. Okay? For the same reasons that we just had for the deviatoric component, the stress that's achieved in equation 5 is a scalar multiple times a dilatational strain or a spherical strain, so the stress itself must be spherical, okay? So I'll just say, for the same reasons as above, the stress produced by a dilatational strain is hydrostatic or spherical. Okay, let me introduce a definition. The bulk modulus, which you've probably heard of maybe back from your fluids class. So the bulk modulus, K, is defined as follows. This is in terms of Lemay coefficients. It's defined as 3 lambda plus 2 mu divided by 3. Okay, that's the bulk modulus. So let's go ahead and we'll call that equation 6. And then substitute 6 into 5. And we end up with sigma ij is equal to 3 times k times Eij. Call that equation 7. One thing to note about a dilatational response is that it's the same in all directions. So sigma 1,1 is equal to sigma 2,2 is equal to sigma 3,3. So we may not want to leave this in terms where there's, and in this case, even if we assume it's symmetric, there's 6 coefficients. We might just want to write it as a single equation. Okay, so we can say that equivalently, we may write equation 7 just by contracting on the index. So instead of sigma ij, we could write sigma ii. Right, so if we write sigma ii, then that's 3 times k times eii, right? Call that equation 8. Right, that's equivalent, and we also haven't lost any information, right? Because those quantities, sigma 1, sigma 2, sigma 3, and epsilon 1, epsilon 2, epsilon 3, are all the same. Okay. So now we have the elastic equations. Now let's talk about extending them to a viscoelastic problem. Okay. So let's say, recall in 1D. So this is a brief reminder of what we've already talked about. That for the elastic case, right? We could write something like sigma is equal to E times epsilon, and in the viscoelastic case, we wrote that sigma as a function of t was equal to the integral from 0 to t of the relaxation modulus y of t minus c times epsilon dot, which was a function of c dc. Okay, so recall that. I'm going to collectively call those equations 9. Okay, so that's the we're gonna make a direct extension of equations 9 now into 3D. So to extend to 3D, okay, we need to treat the 3D equations, 3D elastic equations, in the same way. Okay, what does that look like? Well, how about for the now we have shear and dilatation components, which we didn't have in one dimension. But for the shear component, we talked about that first. That said Sij was equal to 2 mu times eta ij. Okay, that's the elastic case. To move to the viscoelastic regime, you might expect then this becomes Sij as a function of time, going to be equal to a hereditary integral from 0 to t. Note that in this case there's a 2 out front, so we'll retain the 2 here. And now I'm going to write y with the subscript of s to remind you that it's a shear relaxation modulus, t minus c. And then in lieu of the where we had the strain moving to strain rate, we still have that, except now it's a tensor form. Okay, it's the deviatoric strain rate, which I will still remind you is a function of c dc. Okay, call that equation 10. And for dilatation, we can do the same thing. For dilatation, we had that sigma ii was equal to 3 times k times eii. Let's go ahead over to here and say now that sigma ii as a function of time is equal to, we still have our 3 out front, 3 times the integral from 0 to t. Now we have a relaxation modulus, y, which is a volumetric relaxation modulus, so I'll subscript it out the v, times t minus c. Now we have eii dot, which is a function of c dc. Call that equation 11. Okay? I'll just say that we can do a similar extension and write the strains if we want. Okay? So we may similarly write the strains as we'll retain the coefficient out front. 2 eta ij is going to be equal to the integral from 0 to t of j, which is the creep compliance, the shear creep compliance now, so I subscript it with an s, t minus c, and then instead of having the total stress term, it's going to be the deviatoric stress term, Sij dot, which is a function of c dc. And similarly, we could have that 3 eii is equal to the integral from 0 to t J, and now this is a volume creep compliance, T minus C, and then this is sigma II dot C dc. Okay, let's call those equations 12 and equation 13. Okay? So that's the extension to 3D. It's pretty straightforward. Remember that YS is the relaxation modulus for shear, so the shear relaxation modulus. Y sub V is the volumetric relaxation modulus, so corresponding to dilatation. JS is the shear creep compliance. JV is the volumetric creep compliance. So there's 4 terms now, where we had only 2 for the 1D case. But you kind of get the idea and the extension that was done. Okay, so that's all there really is to developing these equations in 3D. We can use them just like we had used all the equations in 1D.